This video explains the different types of code coverage. To measure code coverage, most people, not knowing better, immediately think of counting executed lines. That is, after all, what you do with a source-level debugger. You step through the code, line by line. Well, most modern design and test languages are free format, which essentially means that if you really wanted to, you could code the entire project on one line. Not that I recommend that you do that, just because you can. So as an alternative, some people would propose that we count statements, which seems more accurate, but truly is equally foolish. So here is the problem. For measurement purposes, sometimes many code statements and lines execute together. Imagine an if statement that has one statement in the true branch and 100 statements in a false branch. Do you want the tool to report execution, or not, of the false branch as 100 times more important than execution of the true branch? Probably not. So the simplest solution, which also produces the most easily analyzed result, is to count code blocks. A block is a contiguous set of code statements that execute together. Either all of them execute or none execute. Either a block executes or it does not. How do we decide what is a code block? Using the definition that a block is a contiguous set of code statements that execute together, the flowbreak statements determine the code blocks. The statement after a flowbreak statement starts a new block because that statement does not necessarily execute with the previous statement. Flowbreak statements are the branching and looping statements and the timing control statements. The rules for determining blocks are more precisely these three. First, all statements between matching begin and end keywords that do not contain a flowbreak statement, or a single statement that could be between matching begin and end keywords. Second, all statements from a begin keyword up to and including the completion of the next flowbreak statement. And third, all statements from after completion of a flowbreak statement up to and including the next flowbreak statement, or until the final end keyword. For this example, block 1 at line 26 is a block that could have been between begin and end keywords. Block 2 at line 27 is a block that is between begin and end keywords. Blocks 3 and 4 at lines 33 and 35 start with the begin keyword and end with a flowbreak statement, here and if statement. Blocks 5 and 6 at lines 38 and 40 are the true and false branches of the line 37 if statement. These branches could have been between begin and end keywords. Block 7 at line 41 starts with the statement after a flowbreak statement, here the line 37 if statement. Block 8 is the implicit else of the line 34 if statement that has no explicit else branch. You can disable scoring implicit else branches with the configuration command set implicit block scoring off. Block 9 at line 43 starts with the statement after a flowbreak statement, here the line 34 if statement. Block 10 at line 44 starts with the begin keyword and ends with a flowbreak statement, here an if statement. Blocks 11 and 12 at lines 46 and 48 are the true and false branches of the line 45 if statement. these branches could have been between begin and end keywords. Block 13 at line 49 starts with the statement after a flowbreak statement. Here, the line 45 if statement. Block 14 is the implicit else of the line 43 if statement that has no explicit else branch. You can disable scoring implicit else branches with the configuration command set implicit block scoring off. The Xcelium integrated coverage does not by default score non-procedural statements. For Verilog, you can score continuous assignments as one block with the configuration command set assign scoring. Be sure to study this carefully, as you will soon be quizzed. No, not really. What you truly need to understand is that the Xcelium integrated coverage does a very good job of partitioning code into blocks. You have no need to understand exactly where each block begins and ends. Expression coverage presents a multitude of issues. Expression coverage is, by default, relatively simple, meant only to potentially identify the condition causing execution to enter a block, so you can initially think of it as being an adjunct to block coverage. The major expression coverage issues are three. What operations are scored? In what statements are those operations scored? And in what detail are they scored? You will see that expressions can be scored in multiple ways. The first major expression coverage issue is what operations to score. The Xcelium integrated coverage scores by default only the logical operations, that is, the conjunction and disjunction operations. That is actually a sensical decision, as it by default scores only conditional expressions, and those expressions are predominantly logical expressions. However, you can set the coverage configuration as needed to also score other operations, such as relational operations. The second major expression coverage issue is in what statements to score expressions. The Xcelium integrated coverage scores by default only the conditional expressions, that is, the expressions that control execution flow. Recall that expression coverage is primarily meant to potentially identify the condition causing execution to enter a block. However, you can set the coverage configuration as needed to also score other expressions, such as expressions generating a value assigned to a signal. For the first example, the Xcelium integrated coverage scores by default only the conditional expression of logical operands. It cannot with any option score the add operation. For the second example, the Xcelium integrated coverage scores if you enable scoring of procedurally assigned expressions, the subterm involving a logical expression. It cannot with any option score the shift operation. If you also enable it to score bitwise operators, it scores the bitwise expression, but by default still treats the terms as logical quantities. I will later show you a way to also score the individual bits of a vector. The third major expression coverage issue is how to score the expressions. For this exercise, consider the expression A and B or C and D. Assume that these terms are vectors, so that we can examine vector scoring. That means that we must enable scoring of bitwise operations. As logical expressions of vectors are less frequent, let us assume that this expression is an assigned value. So we must also enable scoring continuously or procedurally assigned expressions, whichever is appropriate for the context. For this exercise, as we have interest only in the scoring method and not in the actual results, we will not provide values to the expression inputs. The Xcelium integrated coverage scores expressions by default in sum of products mode. The sum of products scoring mode checks that each input has attained both the 0 state and the 1 state. It is essentially a toggle test for the expression inputs. Sum of products scoring is naturally first level, but does break into sub-expressions an overly complex expression, or as needed to migrate arithmetic or relational expressions to the lowest level. Sum of products scoring treats this expression as a single-level expression of 4 logical terms. You can optionally select the control scoring mode. The control scoring mode checks that each expression input has controlled the expression value. Control scoring is naturally multi-level. It breaks expressions into sub-expressions as deeply as needed to evaluate each controlling term. Control scoring treats this expression as a multi-level expression of 4 logical terms. You can optionally select the vector scoring mode. The vector scoring mode is an extension of control scoring that treats terms as multi-bit vectors instead of logical quantities. It simply does control scoring for each individual bit position. Vector scoring treats this expression as a multi-level expression of 4 vector terms. As the vectors are 2-bit, the number of scored table rows per sub-expression has doubled from 3 to 6. You can optionally select the full combinational coverage mode. The full combinational coverage mode is an extension of vector scoring. It checks that every possible combination of expression input values has occurred for every bit position. As these are binary expressions, the number of scored table rows per term bit position has increased from 3 to 4. For toggle coverage, the issues are only 2. The first issue is, what do we score? For VHDL, we score entity ports and architecture signals of Boolean, bit, and standard logic types, and bit vector and logic vector types, and records of these types. For Verilog, we by default score module and interface ports, nets, and variables of bit and logic types, and bit vector and logic vector types, and structures of those types. We do not score numerical types, such as integers and reals. For System Verilog, the coverage configuration command set toggle scoring can score additional items. Use it with its System Verilog multidimensional array option to score static multidimensional arrays of the supported types. Use it with its System Verilog enumerated types option to score enumerated types, in which case a full toggle is when the variable has attained all defined enumerated values. Include its System Verilog structure with enumerated types option to enable scoring structure fields of enumerated types. The second issue is, what transitions are toggles? Toggle coverage is simply, did each signal toggle up and down? It gets more interesting when, as any good lawyer would observe, That depends on what the definition of up and down is. As you might imagine, we score transitions from a binary state to the opposite binary state. Each direction is a partial toggle. Two opposite direction partial toggles are a full toggle. With the configuration command set toggle include Z, we also score toggles from the high impedance state to a binary state, but not the other way around. And with the configuration command set toggle include X, we score toggles from the unknown state to a binary state, but not the other way around. Remember that each direction is a partial toggle. Two opposite direction partial toggles are a full toggle. This applies to transitions that originate in binary states and also transitions that originate in the high impedance or unknown states. Toggle coverage is useful to detect interconnect problems. You hopefully do not have too many of those. Toggle coverage is the only code coverage you have available for a gate-level net list, which is essentially all just interconnect. For state machines, the one overriding issue is that the Xcelium integrated coverage must be able to statically recognize that the sequential code block represents a state machine. So your state machine must comply with all the requirements for logic synthesis, but beyond that, must also statically look like a state machine. The code block that tests the current state, be it the combinational block in the two-block style or the single-block style sequential block, must be a case or if statement that compares the current state to constant values and assigns constant values to the next state. Except for a strictly coded Verilog one-hot machine, these assignments must be to the whole state vector, and not only a bit select or part select of the state vector. If the state machine is extractable, then you can obtain automatically instrumented coverage for state visitation, optionally including reset states. Reset states are states entered dependent solely on inputs and independent of the previous state. State transitions, optionally including transitions to reset states, and optionally including hold transitions, that is, transitions to the same state. And arc coverage. Arc coverage is transition coverage that includes controlling expression term values to inform you why the state transition occurred. If the state machine is not extractable, then you can still obtain automatically instrumented block, expression, and toggle coverage, and user-defined value and value transition coverage of the state vector. Here are some examples of bad and good state machines. The left machine is described at the behavioral level of abstraction. A logic synthesis tool cannot infer logic from this description. The right machine is described at the register transfer level of abstraction. A logic synthesis tool can infer sequential logic from this description. However, ability to infer sequential logic does not by itself guarantee that the tool recognizes it as a state machine. The left example outermost branching construct tests the inputs. A logic synthesis tool may infer sequential logic from this description, but will not recognize it as a state machine. The right example outermost branching construct tests the current state. A logic synthesis tool will recognize it as a state machine. The state machine is extractable. The left example assigns values to individual next state bit selects. A logic synthesis tool may infer sequential logic from this description, but will not recognize it as a state machine. The right example is in a very strict one-hot style. A logic synthesis tool will recognize it as a state machine. The state machine is extractable.